So for this problem here, first we need to decide which integration technique do we want to use to evaluate this integral. So you can pause the video here, decide which method you're going to use, and go ahead and solve it, and then I'll come back. Now the obvious method to solve this particular problem is your standard U-substitution. Anytime you have a portion of the integral, in this case the denominator, where if you look at the radicand, the derivative is 2x and there's an x on top, that always suggests that the U-substitution is going to work. Now I'm going to work this one two ways, starting off with the U-substitution, just to show you the difference, because a lot of times there's going to be more than one way to solve a problem. You might pick the harder one or the easier one, or there might be an easy way, but the instructor wants you to work a certain way just to see if you can do it the long way. But here, I'm going to let u equal to x squared plus 9, which of course is the radicand here. So du will be 2x dx. So notice here, I can solve for dx, make a substitution. The next step, of course, is to convert this to an expression involving u instead of x. So I could just say x dx divided by 2 here will give me du over 2. So then I come back over here for this integral then. X dx can be replaced by du over 2. So I'm going to put du here, and I'll put the 1/2 out here. And then in the denominator, x squared plus 9 can be replaced by u. And then instead of the radical, I'm just going to put to the 1/2 power. This is then equal to 1/2. And then bringing this to the numerator, change the sign of the exponent. This would be negative 1/2 here, du. And now it's a very basic integration here, using your power rule for integration. Adding 1 to the exponent here gives you 1/2, and then dividing the coefficient by 1/2. The 1/2 cancels, so I get u to the 1/2 power plus the constant of integration. Convert back to the original variable, and of course u is x squared plus 9. So I could write this x squared plus 9 to the 1/2, or I can put it back in terms of radical plus c. And that's the easy way to solve this one. Sometimes the u substitution won't work, so you might have to use partial fractions, a trig substitution, integration by parts, and so forth. But in this case, this is it, and this pretty much completes the video. But if you want to see how the difference between this and a trig substitution, we'll keep watching. So this is your answer here. Now I'm going to do it by using a trig substitution. Trig substitutions, you have 3 main ones, one involving the sine, one involving the secant, and one involving the tangent. So you use the tangent one anytime you have the square of a variable. It could be it's x squared, and of course the u would be x. The a squared here, in our case it was 9, so it's 3 squared. The a is 3, and you set up this triangle right here. The tangent of the angle is u over a, and you make this substitution here. Or it could be one of these other two over here that we have. Procedure is very similar. We have x squared, the radical here, and this could be in the numerator, it could be in the denominator. It might not even have a square root there, as long as it's in this format, x squared plus 9. So in this case, the u in the setup that we looked at would be x, and the a would be 9 squared here, so 3 squared is 9. The a would be 3. So the triangle that we're going to look at is this one right here. this angle then I'm going to call theta, and tangent of theta is x over 3. And then this side, of course, is the square root of the squares, sum of the squares here, x squared plus 9. So I get the hypotenuse is equal to this. So now from that information here, then we go to the setup here. And just to save us time here, I set it up. So from the triangle, the tangent of theta is the opposite over the adjacent. So that was x over 3. And then all I did here in the next step is solve for x, multiplying by 3, x is equal to 3 tangent theta. And then I went ahead and took the differential here, dx is equal to derivative of tangent is secant squared theta d theta. So that means where I have an x in the integral, the integrand can be replaced by, or the x in the integrand can be replaced by 3 tangent theta. The dx can be replaced by 3 secant squared theta d theta. And then for this radical, I have the square root of x squared plus 9. But the x is 3 tangent theta from the substitution we just did. And that's squared plus 9. So notice here, 3 squared is 9, tangent squared is tangent squared, so that'd be 9 tangent squared theta plus 9. Here I factored out the 9 here from this radicand. Root of 9 is 3, and that leaves me with tangent squared theta plus 1. That's one of your basic identities. That's secant squared. Okay, so this comes out to secant squared. Factored out the 9 square root of 9 is 3. And I got tangent squared theta plus 1. That's secant squared. And the square root of secant squared is secant theta. So then I just made the substitutions here. So x replaced by 3 tangent theta. Dx, from right here, is replaced by 3 secant squared theta d theta. And of course, the radical simplifies using trigonometry identities to 3 secant theta. And then here, you can reduce this. And here, secant cancels, so I get 1 here. So that leaves me with the integral of 3 tangent theta, secant theta, d theta. And then I go to the next step here. 3 tangent theta, secant theta, d theta. All I did here is I said tangent of theta is the same thing as sine over cosine. And secant is 1 over cosine. So I multiplied the cosines and I got 3 sine theta d theta over cosine squared. And actually to complete it now, I have to go to the standard U-Substitution. So in these steps here, I use this factor here. I let u equal to cosine theta. Then du is equal to minus sine theta d theta. The derivative of cosine is minus sine. So that's why I get this right here. And then it's just a matter of substituting. So notice here, sine theta d theta, solve for that, that's going to equal to minus du. If I multiply by a negative here, this becomes a negative over here. So that's this part right here then, in the numerator, became a minus sine, or I should say it became minus du. The sine theta d theta is the same thing as minus du, and of course I had the 3 there. So I get negative 3 du, and then of course the substitution is u is equal to cosine. So instead of cosine, I have u, and that's squared. And I take this up to the numerator, I get negative 3 u to the negative 2. And then again, simple integration, add 1 to the negative 2. I get a negative 1, divide by negative 1. This becomes a positive 3. So we get this, plus the constant of integration. And then I go back to the original variable. For this substitution, I go back to the original variable, and that is theta. So the u is replaced by cosine theta, negative 1 plus c is equal to. But now we have to go to the real original variable. We start off with x. For this part here, I go to the triangle. So from the triangle, I find cosine of theta. So cosine of theta is the adjacent, which was 3, over the hypotenuse, which was the square root of x squared plus 9. So that's how I got this right here. And then just to the negative 1. And then, of course, to go from this step here to this step right here, this is a negative 1, so that's the same thing. If I make it a positive 1, I have to take the reciprocal of this. So it actually becomes applying that negative 1 exponent, it becomes square root of x squared plus 9 over 3. And then, of course, it's multiplied by 3. So these divide out. And I get the answer, the square root of x squared plus 9 plus a constant, which is the same thing we got using your standard U-substitution applied to the original integral. But you can see the difference in this case. If you have a choice, you want to take the easier route. Thanks for watching. We'll see you next time.